The European People Group for Particle Research, CERN, is uncovering nuances of another iota smasher today, something on numerous occasions greater and twice as significant. It has found 3 new particles that could help us with sorting out how our universe was considered and what its future resembles. Specialists at CERN have, as of late, uncovered revelations that turn how we decipher the universe on its head. Beneath the outer layer of their weighty tests lies a vast expanse of particles and powers so odd they could be straight far away from potential sections to various perspectives, to particles that challenge the actual basis of reality. What confusing secrets are covered inside these tests? Could we hop into the universe of CERN and unravel the pieces of understanding that could reevaluate our universe? The entryway to new viewpoints. A wormhole could speculatively appear unexpectedly overhead, and the explanation would be the memorable assessments led at CERN, home of the immense Hadron Collider, LHC. The LHC is the world's greatest and most impressive iota smasher, found near Geneva, riding the line between Switzerland and France. There are secrets about this bizarre affiliation that the world has barely any insight into, secrets that could really change how we view physics in the universe. CERN, the European Relationship for Nuclear Exploration, works this colossal logical instrument. It reaches out over 27 kilometers and sits deep underground. The primary function of the enormous Hadron Collider is to allow physicists to test the gauges of various theories of particle material science. This includes the high-profile assessment of the Standard Model of atom physics, which helps us with sorting out the essential structure blocks of the universe. At its center, the tremendous Hadron Collider works by accelerating protons to practically the speed of light prior to smashing them together. These effects produce a shower of new particles, which specialists review to gain insights into the laws of nature. It was through such preliminaries that the Higgs boson, commonly referred to as the God particle, was found in 2012. This disclosure confirmed how particles acquire mass and was a significant moment in atom physics. The tests conducted at the enormous Hadron Collider are huge for sorting out characteristics that occur under silly conditions, equivalent to those not long after the Big Bang. The data assembled can fill us in more about how the universe started and evolved, and about the fundamental constituents of matter. This makes the gigantic Hadron Collider a player in potentially uncovering new aspects of reality, angles that could make sense of mysteries surrounding dark matter and the fundamental forces of nature. Such high-level experimentation at CERN doesn't come without stresses. Some speculate about high-energy tests creating dark holes or exotic matter that could present threats to Earth. However, CERN ensures that all safety measures are met and established. Analysts closely monitor these assessments, reviewing and certifying speculative models to confirm that any risky circumstances are highly improbable. Through its consistent assessment and disclosures, CERN helps us understand the universe better and showcases the unbelievable capacity of human imagination and cooperation in pursuing knowledge. The LHC is humanity's current wonder. The gigantic Hadron Collider at CERN isn't just a remarkable piece of technology, it is a marvel of modern science and engineering. Located under the Swiss-French border, the enormous collider goes through a tunnel 27 kilometers in diameter and is as deep as 175 m underground. This makes it the largest particle collider on Earth and one of the primary instruments in the field of atom material science. The development of the immense Hadron Collider is designed to handle assessments of remarkable scale. The chief ring of the collider, housed in a tunnel with a width of 3.8 m, contains 2 connecting equal beam pipes. Each line coordinates protons in backward bearings, accelerated rapidly by a series of superconducting magnets. These magnets are fundamental for maintaining the path of the protons, bending their course at speeds close to that of light. Enveloping the beam pipes are layers of cooling systems that keep a temperature colder than space, necessary to maintain the superconducting magnets at their required operating temperature. The size of the colossal Hadron Collider is further highlighted by its use of thousands of magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The largest and most powerful superconducting magnets used are 15 m long and weigh 35 tons each, showcasing the immense physical scale and innovative ambition behind the colossal Hadron Collider. The principal job of the huge Hadron Collider is to examine the fundamentals of the universe by seeing the smallest pieces of matter. By accelerating particles to nearly the speed of light and then colliding them, the gigantic Hadron Collider allows physicists to concentrate on the subsequent particles produced during these impacts. This process aids in testing and expanding our understanding of the standard model of atom physics, which is currently the best depiction of the subatomic world. One of the key objectives behind the gigantic Hadron Collider's tests is to uncover the mysteries of the Higgs boson. Its revelation at CERN in 2012 confirmed speculation about how particles gain mass. The tremendous Hadron Collider also investigates other key particles and forces, looking to resolve fundamental inquiries like the presence of dark matter and the nature of the universe, not long after the Big Bang. Furthermore, the gigantic Hadron Collider hopes to confirm the presence of new particles that speculative physics predicts, but has not yet observed. These investigations are crucial for potentially discovering new physics beyond the standard model, including supersymmetry and dimensions beyond the usual three-dimensional angles. The vision behind the gigantic Hadron Collider isn't just to sort out the universe's structure, but to foster global cooperation, with thousands of scientists from over 100 nations collaborating. The colossal Hadron Collider is proof of overall cooperation in the quest for knowledge. Its design and scale enable it to tackle some of the most pressing questions in physics. Its inspiration extends beyond simple scientific curiosity, aiming to enhance how we interpret the universe and inspire global collaboration in science. Through this gigantic and complex apparatus, humankind continues to push the boundaries of what is known and ventures into the quantum realm. But how does the gigantic Hadron Collider genuinely work? At the core of CERN's research facilities, the enormous Hadron Collider serves as a powerful magnifying lens into the quantum realm, allowing scientists to observe and study the fundamental particles that make up everything known to humanity. The process of particle acceleration and collision at the gigantic Hadron Collider is a vital procedure for testing the underpinnings of physics. Within the collider, two high-energy particle beams travel at nearly the speed of light before they are made to collide. These beams travel inside tubes maintained at ultra-high vacuum, recreating the conditions of space. Superconducting electromagnets, cooled to temperatures colder than space, guide and focus the beams at designated collision points along the tunnel. These beams collide with gigantic energy, producing a variety of subatomic particles, some of which are extremely unstable and exist only for fractions of a second. To identify and analyze the results of these collisions, the enormous Hadron Collider is equipped with massive detectors, ATLAS, CMS, ALICE, and LHCb, each designed for specific types of research. These detectors capture data about the particles, including their mass, charge, and energy. This data assists physicists in testing predictions of atom physics theories, including the Standard Model, and investigating particles and forces that govern the universe. One of the most critical discoveries at the gigantic Hadron Collider was the discovery of the Higgs boson in 2012. This particle, sometimes referred to as the God particle, is significant because it provides evidence for the Higgs field, which is responsible for giving mass to fundamental particles. The presence of the Higgs boson was predicted by the Standard Model, and its discovery was a phenomenal achievement, confirming long-established theoretical predictions. Beyond the Higgs boson, the tremendous Hadron Collider has also been instrumental in discovering a range of different particles. For instance, the collider has provided evidence for the existence of pentaquarks and confirmed the existence of tetraquarks, particles composed of 4 and 5 quarks, respectively, which had not been seen before. These discoveries expand our understanding of hadronic matter, which is matter made of quarks bound together by strong forces that keep the nuclei of atoms intact. These discoveries showcase the predictive power of the Standard Model and also open new avenues of investigation in particle physics, offering insights into the behavior of matter under extreme conditions like those soon after the Big Bang. Speculative risks, however, continue to be a topic of discussion and investigation as the capabilities of the gigantic Hadron Collider evolve. Two of the most debated speculative risks associated with the Gigantic Hadron Collider are the creation of strangelets and the possibility of generating tiny black holes. These scenarios have captured public interest and scientific scrutiny. Strangelets are a hypothetical form of matter that is more stable than ordinary matter. The theory suggests that strangelets could convert any matter they come into contact with into strange matter. The fear associated with this theory is that if strangelets were produced during particle collisions at the Gigantic Hadron Collider, they might actually— Note: the text cuts off here. If you would like me to continue or make any other changes, please let me know. They might actually pose a threat to ordinary matter on Earth. However, physicists generally agree that the likelihood of this occurring is extremely low. The conditions required to produce strangelets are not present in the collisions conducted at the LHC. Similarly, the idea of creating tiny black holes has sparked significant debate. Some theories suggest that high-energy collisions might produce micro-black holes, which would evaporate almost instantly due to a process known as Hawking radiation. While intriguing, the consensus among scientists is that these micro-black holes would not pose any danger to our planet. CERN has a robust safety protocol in place, ensuring that all experiments are conducted under stringent safety standards. Extensive reviews and assessments have consistently demonstrated that the risks associated with high-energy physics experiments are negligible. In fact, the scientific community widely supports the work being done at CERN, recognizing its potential to unlock new frontiers in our understanding of the universe. In summary, the Gigantic Hadron Collider at CERN is not just a monumental achievement in engineering and science, it represents humanity's quest for knowledge. It allows scientists to explore fundamental questions about the universe, including the nature of matter, the forces that govern it, and the origins of the cosmos. As researchers continue to analyze the data and uncover new particles, the potential for groundbreaking discoveries remains vast. Through international collaboration and innovative research, CERN stands at the forefront of particle physics, pushing the boundaries of what we know and expanding our understanding of the universe. The work done at CERN not only has implications for science, but also inspires future generations to explore the mysteries of our existence.